Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on structural systems in architecture. The module 5 is going on, and this module 5 is on the truss and the space frame. And in the module 5 we are in the third lecture, and this is on the analysis of truss part 2. So, in this lecture we will going to have the truss framing system. We will discuss that how the framing system of the truss is being adopted, then the classification of the truss system, and then some of the numerical analysis of the truss. So, the learning objective of this particular lecture is to outline and classification of the framing system, and the analysis the force distribution of the truss due to a given geometrical patterns. So, if you see a truss which we have discussed so far is the individual truss and to how to analyze the individual truss and what are the different parts of the truss, the geometrical formations also. But you remember that a particular truss, a single truss cannot be serve the purpose. It has to be taken into the series of truss which may be of similar of kind, or maybe some differential the changes in the geometry, and that has to be placed one after another in some spacing or some distance apart, and the whole building roof can be actually taken into account. They integrate in a total way. So, in that, if I see that particular 3 trusses are here in this particular figure are placed as a separated some distances, that separation distance between one truss to the other truss is called spacing of the truss. And the span of the truss already you have discussed, that is the from one support to the another support, what is the span. So, these trusses will be supported by some pillars or some columns like this, by some other structural members like column or maybe wall or whatever, and these 3 truss will be now has to be integrated by virtue of some other structural or some non-structural members. So, if I see this particular truss as in a isometric view, I can see in the plan as a 3 lines only, right. The 3 lines are as having a separated distance between the spacing also. So, I can say that this is the span, this is the span of the truss, and this is the spacing of the truss, right. This is the spacing of the truss as per my plan view also. So, next if I go further, so this is the how the plan showing the spacing and the span. Now, these 3 trusses are has to actually tie with some other members. So, those trusses in those nodal points, you see those blue lines, horizontal lines are taken, those are called purlins. So, those are the connecting member between one truss to other truss, and that will give a kind of a smooth the surfaces. Of course, the smooth surfaces has to be created over that, and that smooth surfaces or maybe another surfaces will be created by virtue of the roof covering, and there are various type of roof covering. So, purlins actually going to help 2 way. One, it will connect from one truss to the another truss. In between the spacing of the truss they will connect. So, they make integrity between the total system, number 1, and number 2, the purlin will transfer the roof load and to the typical nodal joint of each and individual truss. So, if I say this, there is a the roof covering. So, this portion is the roof covering. So, total roof covering, the load of this roof covering is actually transmitted by this 1, 2, 3 and 4 purlins to the particular truss itself, the portion of this 4 nodal point. And now we can find out the what is the load and what is the total amount of the dead load, live load and the wind load and all, and you can find out and we can give those particular value of the load to this particular 4 points. We will discuss this thing in the next lecture in the application of the truss in the architecture in that particular category. We will 3 slides we will discuss on that how the load transfer mechanism is going to take place. Now, if you see now the plan view, it will be look like this, but this plan view are these lines are now are the truss the purlin lines, and this is the truss line as I have discussed, the span of the truss, spacing of the truss and the truss line. Now, sometimes this is fine, sometimes if the wind is not so much, if there is a kind of a jump, the span is also not that much high. So, only purlins can take care and you can just put your roof covering over there. But sometimes when you expect a high wind load, maybe it is very near to the coastal area, very high wind zone, or sometimes span is very high or whatever, it is in an empty area or the large span and all, and maybe there are some amount of some other loads are also there for industrial load like a gantry girder or something like that, then only purlins, the straight purlins will not going to help you, then you have to go for the diagonal top bracing. So, this see the red lines, those are the bracings, those are the connecting members diagonally from one truss to another truss, and that also connect from the nodal points. So, additional to the purlin, we provide some kind of a diagonal kind of a bracing, and how many bracings and what will be the size of the bracing has to be definitely find out from the some mathematical the load distribution and the mathematical computation. So, now if you see the plan, there are diagonal red lines are also come into the picture, and those red line indicates the diagonal bracing of the truss. But this is called top chord plan, because it is whatever I have drawn over here, these purlins and the diagonal bracings are actually placed over the top chord or the 2 sloping portions of the trusses. But sometimes this is going to be the end of it, because these diagonal bracings and purlin, those combinations can hold the system good under the heavy wind load or under the large span kind of a criteria. But sometimes that may be insufficient, wind load may be further high, you need much more robustness in your system, you need much more connectivity in your system to make it stable under those kind of a fluttering wind and all. So, then we have left out with the bottom chord. So, now you see in the bottom chord you can place the purlin. So, the connecting member in the bottom chord connecting members, which may not be called as a purlin, but it is something like a horizontal members, which is the bottom chord purlin member you can say. So, that can be placed, and also you can place some the diagonal bracing in the bottom chord also. So, now if you do that, then you have to draw the bottom chord plan also, which shows the connecting bottom connecting member and also the diagonal bracings at the bottom. So, what happened is that you have to perhaps you have to draw 2 plans for a particular system of truss as a top chord plan or the bottom chord plan. So, that is, and finally, this will be the end of it, because now you are not left out any other surfaces. So, if you want to further see that the stability problem or something like that. So, what you have to do, you may change the pattern of the truss. So, instead of this pattern you can go with some heavy type of truss, or you may decrease the span of the truss, or sorry, not the span, the spacing of the truss. Why spacing of the truss? So, the individual load on the particular truss will be less in that case, and you can have the stability. So, number of trusses will increase in a particular the length, and definitely the load sharing also will be decreased per truss also, right. So, this is the framing system. And what are the steel sections are used for the truss? Those are the typical 3 types of steel can be used. One is the single section used, that is light sections like angle section, T section, circular pipes, or the square hollow sections or square rectangular hollow sections, which is this these sections are the square rectangular hollow sections, this is the angle section, these are the channel sections can be used easily. In case of the channel section, if you use, you can call it as a heavy section, sometimes I section can be used as some of the members, or you can use the 2 channel sections and make a kind of a box. So, something like this, which is called as the built up sections. So, we can have 2 angle sections to create the inverted T. You can actually make a box out of 2 channel sections, the second one, and we may go with a heavy sections made up by 2 I sections and a 2 plate in the top and bottom. So, those are the typical the built up sections can be formed, and we can have those sections as the members of the truss. Now, these are very popular. These the light sections are very popular. The designer try to make or try to build the truss with the help of this the angle T or the box sections also. First they will try to make it with the angle and then the T and the box sections. The pipe, the circular hollow pipes are also used for a lightweight kind of areas or lightweight trusses also. But those built up sections are definitely used. Built up sections are those kind of built up sections. The 2 angle sections are converted to a box, are used for many times in the auditoriums and all. But the last one, the third one, heavy, those heavy sections are used for the railway bridge or those kind of trusses. Now, the classification of the truss system, this is very interesting. So, if you see the the typical geometry of the truss, the profiling of the total truss, and finally your purlins and your the diagonals, and finally how your total the form is look like, if you see, and again you can, if you come back to the individual truss, you can understand the system of the truss, and the system of the truss system can be categorized into the 3 types, and this truss system are actually for the 2-dimensional truss system. For the 3-dimensional truss system, like the space frame system, we have another category. The first category is called the flat truss system. In the flat truss, there are 4 such nomenclature. We will discuss with the figure in the next slide. The second one is called the transmitted flat truss system. So, these are having 3 type of the further category or the subcategory, and the last one is called the curve truss system, which is have another 4 category. So, if you see the first or the second line here, the 3 type of system, one is flat. So, I understand in that particular system we will have the truss as the what we have still have discussed, the parallel cut truss or the inclined or the pitch truss or those kind of flat truss. The second one is the flat truss system, but it is a transmitted or kind of a system. So, it is the one flat and another flat has maybe it is provided in a linear or maybe some angular kind of a folds or in a direction. So, that is a transmitted kind of a flat truss systems over there. And the third one is as usual, it is the curve kind of a truss system. So, let us go further in details of these 3 type of truss system. The flat truss system, as you see, it has 4 type, the top chord, bottom 2 chord or the camber. So, the top chord systems are like a plain 2 type of truss system. So, the top chord are taken care of the all the roof covering or the membrane kind of a thing, whatever we are going to provide for the any kind of the profiling or the kind of the covering of the roof. The bottom chord system is that the top chord is now flat. You see, in the top chord system, the bottom chord is flat and the top chords are making inclinity or maybe a curvature, but the bottom chord system is just opposite, where the bottom chord is a curve or so, and the top chord are making out of flat. But this bottom chord system is not so much popular or not so much adopted in the buildings or built environment. These bottom chord systems are much adopted in the bridges, particularly the second one and in the third one is much has a much applicability in the bridges also. Then the third one is the two chord system, where both the chords are having non flat or the inclinity is also. So, these systems are also used in the buildings, particularly in the auditoriums or maybe in the airports and the large span structure galleries also, where these two systems can be used for the advantages, getting some advantages. One of those system we will discuss in the next lecture. And the cambered system is that, as it is something like it is flat or non flat both the side, but it is a kind of elevated the topmost the bottom chord is bit of elevated. So, that is called the cambered system. And then the next part. So, next part, if I again go back. So, this is some kind of the transmitted system from the flat system is the linear, folded and the intersecting system. So, a linear system, you see it is system which is with a parallel chord, or maybe it is the pitched kind of a roof, but it is a linear, it goes flow with a kind of a one linear 2D plane. So, and then second, the same kind of the truss with maybe it is maybe zigzag or maybe any kind of a profile, but those are one after another is very much linear kind of a in order. The second one is it is non-linear, but it is something like a folded system. So, you have the one set of system, one set of truss and another set of truss. If they go like that, that is a linear, this is the linear, this is going as a linear, but if it is intersecting like this, if it is intersecting like that, then it is a folded kind of a system. And finally, it is intersecting in other way around. So, this first one folded is the intersecting in a line, and second one it is intersecting in a body. So, if it is intersecting in the body or the through its the center point or so, then it is the intersecting system of the truss. All the linear, folded or the intersecting kind of system, we use it for our built environment or the buildings also. The third one is the curve system. So, curve system has four typical types. In that four typical types of the curve system, we have the single curve, we have the saddle kind of a curve, we have where there are the changes of the slope also. In our the seventh one, where we will going to discuss no, it's not seventh one, in the sixth week, when we will going to discuss the different type of the shell structure, we will discuss thoroughly with the saddle shape and those kind of a shape, dome shape also. So, single curve, then if there is a double curve, there is a saddle shape, there is a dome shape kind of a scenario, and or maybe a spherical kind of a the truss system can be also thought of. So, those are come under the category of the curve truss system. So, next let us go to the end of this particular lecture is some numerical analysis of the truss. So, in that we will actually want to see that how the geometrical pattern of a truss and also the support system will actually influence the internal the forces of a particular distribution of the forces. So, already we know from the last lecture how to analyze a truss by virtue of the section or maybe by the joint method. So, in this lecture, in this particular portion of this lecture, we will take two or three type of truss and we will judge these two or three type of truss and see the how it's behave. So, in the first case we have taken the truss number 1 and truss number 2, that one is the pad truss and the second one is the fan truss, and both are having 6-meter long span and 2 meter is the rise, and the loads are also very similar. So, the loads are all, you see the 50 kilonewton here also, this is also coming under the 50 kilonewton. And now let us see that which one behaves better, or are they same in the nature also. So, a 6 meter span and the 2 meter. So, I solved both the trusses by virtue of the joint method, and I found the forces like this. So, I have noted down it, and this is symmetrical. So, the forces are also very much symmetrical. And with this particular 2 diagram, it is sometimes very confusing, it is all the numbers and all. So, what I did is that I redraw these 2 figures with making this the blue or the purple color. The purple color, the members are compression members. So, those are the compression member, and the red color members are the tension member. So, you see in this trusses also, as it is some behaving like a beam. So, as you know, if you put the load from the top to a particular beam bends, and due to the bending of the beam, the topmost portions comes under the compression and the bottom part of the beam comes under the tension. It is also something like that. So, the compression and the tension is created by purely it is created by the topmost portion and the bottommost portion. The bottommost portion and the tension here also in this fan truss also, and topmost portions are under the compression. So, this is exactly how it is behave in a beam, but you see the internal members which are the post or the stud or so, they behave differently. So, here you see the post are mostly compression, posts are also mostly compression, but here you see this post, 2 posts are in, I am sorry, this posts are under tension here, sorry, and this posts are compression, the behavior changes, whereas this studs are under compression, purple color, but here studs are compression also, tension also. So, the one thing is very clear to me or clear to us is that under the gravity load, under the downward load, a truss mostly behave like a perfectly behave like a beam. The topmost portion rafters are in compression, tie beams are under tension, that is why it is called tie beam. But internal members, post and the studs behave differently because of the geometrical changes, orientation changes also. See, there is no change in the span, no change in the rise, no change in the loading, only change in the orientation of the internal member. So, the actual triangles, the big triangles are same both, only changes is made in the this particular the changes in this kind of the internal post and the stud. So, those are bit confusing in the sense it sometimes because of some orientation take compression, and sometimes the same post maybe the same height also can take the tension also, right. So, this is, and if I compare with some kind of a the table format, this is the truss 1 and the truss 2, we see it is almost same. I have also computed the total length is almost same 23.5 meter, 24.4 meter, just 1 meter difference, that is not issue at all. And the forces, if you see, this is almost if you just put on the, if I just highlight with some kind of highest forces, here is maybe 45, this is 45 highest, here also it is 45, same, the highest forces there is no change. And if you see the lowest force is 5, and here it is lowest force is 9, which is comparable, which is very much. So, there is not so much of change in the force, the highest. So, the design will be almost the same, the amount of steel required for both the cases will be mostly the same. There is not at all any kind of the benefit that you can get if you use it or this or that. So, or other type of trusses, the truss 1 and truss 2 gives you mostly the same typical type of solutions in these 2 cases. Now, let us go to the another set of trusses. So, this truss A, if you remember in the last lecture we have solved this kind of this truss. That you see that the span of this truss is each panel is of 2 meter, it is a parallel chord truss 2 meter, and this total span is 8 meter, and the depth is 1.5 meter, and the supports are at the extreme end, the L1 and L5, the forces are given to you. This is the truss B, which is also we have solved in the last lecture. The same span of each panel of 2 meter of 8 meter of span and 1.5 meter of depth, and it is also having the simply supported at L1 and L5. So, we have solved that one also. So, I have taken these two truss all together. Now, let us see the what is the phenomena, what is the change in this particular. So, if you go to the top chord, you see the top chord are always under compression and the bottom chord is tension. This is, see, the bottom chords are in tension, top chord are under compression, both the cases. Here I will get as null force, 0 force. So, the bottom chord are tension, top chord are in compression, top chord are in compression, bottom chord are in tension. So, this follows the pattern of the beam, the system of the beam, that is good. Post are under compression and the diagonals are under tension. Let us see here, it does not have any post because all are diagonals. So, in that there is a mixed variety, and if you go to this, you will see that there is a tension in this, there is 0 almost over here, and there is alternate compression. So, the compression alternate, and this you can say this is tension, it is 0 and this is tension. So, there is a alternate the changes in the compression and the tension which should be looked into, which should be understood that the middle portion has to be, we have seen the other cases also, that the pitch truss also the internal forces are either compression or tension, and there is a kind of a symmetry, there is a kind of a rhythm in it. If you go to the truss A, you see tension, tension, tension and tension, whereas this is compression, compression, post are in compression. So, there is a kind of a rhythm, kind of a symmetry in it. So, we can understand that from this particular virtue of this particular two type of trusses, they behave similarly. Now, if you see the with the highlighter, if you see the what is the forces and all. So, let us take the highest force, that is 26.67. Here it is 24, no, it is 30. This is 30, comparable 26 and 30, but it is in diagonals, but in that case it is in top chord. That not an issue, because that finally which will be giving you the final dimensions and all by virtue of the highest forces also. Lowest force 0 is of course lowest, but the other than that 0, this is 8.33, and here it is 16, here it is little bit high 15, here it is 15 is the lowest, 15 is the lowest. So, it has a high variation, but it is very much compact, this particular the truss B is bit of compact. So, other than that there is nothing short of changes. So, let us go to another two set of truss. I have again go with a A1 and A2, which is a typical variety of truss A because if you see, this is a truss A is having 8 meter span and 1.5 meter of the depth, 1.5 meter of the depth. Here also I kept it 2 meter of the depth and the 8 meter of the span. So, only change is that the depth is increased by 500 mm. Loading, everything is geometry is same. So, definitely there will be some changes in the forces, and there is a truss A2 also. In A2 what I did is that I have pushed the support to the L2 and L4, not in L1 and L5. So, this portion is cantilever portion, this portion is the cantilever portion, and this is the simply supported portion. So, the span of the truss is reduced to 4 meter, and the 2 meter and 2 meter is the two overhang in that. Loading and the depth is kept as A, that is 1.5 meter, and I again solve this particular this thing. So, if you see one interesting change over here is that with respect to this, you see this is your all compression at the top, which is all compression at the top, but here you will see there is a tension force came. So, let us go to this analysis part. So, this is my the 2 meter depth and this is my cantilever one. So, if you see the first one, this is all compression. Here this is also compression, because of course there are two null forces, that not an issue at all, but you see with compared to this, it has top chord is having compression and also 0. Let me check with this. Truss A2 is having some, I think this is not compression, this is there is a small mistake, this is tension, that is the important part of it, this is tension. So, see in the top chord you will have some tensile force in the cantilever portion. So, cantilever portion is having some kind of a tensile force, and the compressive force comes in the tie. Compressive force comes in the tie. Please, this is a mistake and this has to be red in color. So, in the PPT I will make that correction. This is tension. This has to be first seen. Simply supported truss, compression in the top chord, bottom chord are in the tension, fine, understand because of the beam geometry. Support changes, now it is like this. These are a simply supported kind of a case. Top compression, bottom tension, top compression, bottom tension. Here top tension and bottom compression. As first notable changes what I found over here. What I found over here is also very symmetry, that is the posts are in compression and diagonals are in tension, which is symmetry, but here things changes. Here posts are also come under the compression or in tension, and the diagonals are also come under the compression or also tension. That is the nature of the forces. If I see, I have found out the first changes. Let us see the magnitude point of view, what is the changes. What is the, how much is the highest force, or the here 26 point. In this case it is much less, and this the 21 point something. It happened to be because I have increased the depth of the truss. So, the highest force is now lower, because 2 meter is the depth. If I further increase, definitely if I again compute, I can get much less than 21.21 or so. It has to be because the now it is the depth increases, give you much more the flex the decrease in the load shear. The lowest force other than 0 is almost 8.33. The lowest force other than 0 is 3.56. So, the lowest is also, there is a variation, there is a, these two are high and these two are bit low. So, if I say this is a kind of a lowest and this is the second one, this is the first one. But now if you compare the third one, that the A2 with the A, see this is 26.67 here, and this is the highest amount of force is 16 only. See the same depth, only with the change in the, only a slight change in the support system gives me the amount of the forces is very low with compared to this, and the lowest force, which is 8.33, here it is remain as 8.33. So, there is a very compactness, or the I can say that the highest amount of forces, the highest force is reduced by a considerable amount in case of by two-way cantilevering of the truss also. So, this is one of the very important thing that what we have understood from this particular analysis of the trusses also. So, we have written over here, truss with higher depth and two-way overhang produce the better result. Higher depth better result, as I understand, because this is your this load is decreased from this point of view. That is why higher depth truss, which is this is 2 meter depth, this is 1.5 meter depth, is better, and the overhang cases also from this 2.66, this is also 1.5 meter, but it is overhang kind of a case. This is the depth. So, this has been further decreased to the 16.67. That is one of the cases where we can say this overhang kind of a truss can produce better result. Of course, these are the tension, these are the tension. I will correct it and I will send it correct it in the PPT. So, that is all for this particular lecture. I have taken the reference of those books to prepare this particular lecture, and the conclusion, from the conclusion point of view, I must say that the suitable framing system is essential for any truss design, and it is an integral part of the truss system. We have seen the different type of the system like purlins and the diagonals are required to make the integrity of a system of the truss. Force distribution in the truss is based on the geometry and the support position, what we have just now understood by virtue of the 3 typical type of geometrical variety and the depth variety and the support variety. From that we can conclude that yes, the distribution of the force distribution changes, pattern distribution changes. So, that is all for this particular lecture. In the next lecture, we will go to the application of the truss in architecture, which will be the 4th lecture in the module 5. Thank you very much.